In the celebrated example of prisoner's dilemma, we have this general scheme where the two prisoners can either cooperate or not, defect as it's called. If they both cooperate, they get some payoff A, and if they both defect, they get a different payoff D, where A is greater than D. However, if they miscoordinate and one of them cooperates and the other defects, then the cooperator gets the lowest possible payoff and the defector gets the largest possible payoff. And that's true symmetrically here as well. And this a very well-known example that has rather counterintuitive paradoxical properties. Most games are not as conceptually confusing. Here's an example that's conceptually very clear, and these are games of pure competition. The situation here is limited to two players, where one player's payoff is exactly the complement of another player's payoff. So they always sum to some constant C. Often that constant is zero, and we call them for that reason zero-sum games as opposed to constant-sum games. And since they do sum to zero or to a constant, we only need to remember one number, the payoff to one of the players, and we can infer the payoff to the other player from that. Here's the most simple version of it. This is games of matching pennies. So you and I each need to pick either heads or tail for the coin. If we pick the same side, either heads or tail, I win, which means that I get a payoff of 1 and you have -1. If we miscoordinate, and so I pick heads and you tail, or the other way around, then you win. A very straightforward game of pure competition. Here's another very well-known similar games with 3 actions for both of us, and that's the game of rock, papers, and scissors, also known as Rochambeau. And so if we pick the same action, then it's a draw. And otherwise, there are rules for who wins. For example, if I pick rock and you paper, then you win. If I pick rock and you scissors, then I win, and so on. Again, the payoffs in both cases sum to 0. Just parenthetically, this very simple children game actually has an annual competition that carries a non-trivial prize of $10,000. And it's actually a sobering thought that when we look at this trivial game and perhaps chuckle a little bit, if we actually participate in this competition, we'd actually think hard about how to play it. Here's the other extreme of games of pure coordination or pure cooperation. In this case, all agents have exactly the same interest. In other words, their payoffs for every action vector that they take is the same. And so the utility for player I is always the same of utility for player J for every action vector that they choose. And so again, here too, we only need to write in each cell of the matrix only one number because it's common to all the players. It drives home perhaps the unfortunate term non-cooperative game theory that describes this dominant strand of game theory we're discussing for now. The name would suggest that these are games that describe situations that are inherently conflictual, but as we see, they apply also to games in which the interests of the players coincide. So here's a game that describes a purely cooperative situation. You and I walk toward each other on the sidewalk. We can each decide whether to go to our respective left or our respective right. And if we pick the same side, then all is good. We avoid a collision. If we don't, then we do collide, and that's equally bad for both of us. Of course, in general, games will be neither purely cooperative nor purely conflictual. And here's a game that exemplifies that. This is a game that's called Battle of the Sexes. So imagine a husband and a wife who want to go out to a movie. There are two movies they could choose from. Let's say Battle of Armageddon and Flower Child. The one a violent war movie, and the other is a romantic comedy. Above all, they want to go together to the movie. If they go to different movies, then they are equally unhappy. So they want to go to the same movie, but they have conflicting preferences. The wife clearly would prefer to go to Battle of Armageddon, and husband, romantic as he is, would like to go to Flower Child. So both cooperation and competition in this game.
Hi folks, it's Matt again, and now we're ready to start solving games and making some predictions of how people will play in different settings. And so we're talking right now about Nash equilibrium, which is probably the most basic and standard solution concept in all of game theory. It's named after John Nash, who was a mathematician at Princeton and actually some years back won the Nobel Prize for his work on this subject. And it's a very basic and fundamental concept. And in order to sort of motivate it, let's start by just talking through a particular game that was described and invented by another famous person. So this is John Maynard Keynes' beauty contest game. So what's the idea here? So let's think of a basic situation that you might be interested in. And this was one that Keynes described in some detail. So the idea was you have a stock, you're holding on to it, and the stock price is rising. That's great. You're an investor. You're trying to make profits off of your stock holdings. And you begin to believe that maybe the stock is too high to be justified by the value of the company. So you're thinking that it's possible that this stock is overvalued. Maybe there's a bubble in the market, and you're starting to think about selling. Okay, well, you'd like to sell it, but you'd like to wait until the price is at its peak, right? So you'd want to wait until the price was just where it's going to hit its maximum before you sold. So you wanted to get out of the market just before the other investors do. So this is a game where now you have to predict what other people think about the stock price and what they're going to do and when they want to get out. So how will they act? How should you respond to that? So this is the basic ingredients of Nash equilibrium are going to be having some prediction of what other players are doing and then choosing the optimal strategy in response to that. So these are going to be two key ingredients that we have. So there's a very stylized version of this, which is known as the Keynes Beauty Contest game. Where did it come from? Well, actually, Keynes described there was a newspaper in England that had a contest where players had to guess which picture of several women other readers would think was the most attractive one. So it wasn't to guess what you thought, but what you thought other people were thinking. So Keynes likened investing to this. It's not only what you think of the stock, but what you think other people are thinking about the stock that's important in driving your decisions. Okay, so this now is represented by a very simple game that is played by many people. So what's this game look like? Each person gets to name an integer between 1 and 100. Okay, so you get to pick a number between 1 and 100. It has to be an integer. So 1, 2, 3, etc. Players are going to move simultaneously. And the player who names the integer that's closest to 2/3 of the average integer wins a prize. And the other players get nothing. So to win this game, you have to guess the average and then 2/3 of it. Right, so you want to be right at 2/3 of whatever the average guess is. So a little bit below the average guess. If there's two people that happen to hit the same integer that's the right one, then ties are going to be broken uniformly at random. So we'll just flip a coin, or if there's three people, we'll roll a dice, three-sided die, etc. Okay, so how would you play this game? You have to think about what other players are going to do and then forecast what you think the best integer is in response to that. Hi again, it's Matt, and now we're talking a little more about strategic reasoning, and in particular, let's go through and analyze the Keynes Beauty Contest game now and talk a little bit about the Nash equilibrium of this game. So remember what the structure of this game was. Each player named an integer between 1 and 100, so you've got a population of players. They're all naming integers. The person who names the integer closest to 2/3 of the average integer named by people wins. Other people don't get anything. Ties are broken uniformly at random. Okay, so again, what are other players going to do? You have to reason through that, and then what should I do in response? So these are the key ingredients of a Nash equilibrium, and the Nash equilibrium is everybody's choosing their optimal response, the one that's going to give them the maximum chance of winning in this game, to what the other players are doing. That's going to be a Nash equilibrium. Okay, so let's take a look. So how are we going to reason about this? Suppose that I think that the average the average integer named in this game is going to be some number x. So including my own integer, I think this is going to be the average. Well, what has to be true about my reply to that? My reply should be 2/3 of x, right? I should be naming the integer closest to 2/3 of whatever I believe the average is going to be. So my optimal strategy should be naming an integer closest to 2/3 of x. So here we're just working through heuristically. We'll get to formal definitions and analysis in a little bit, but let's just go through the basic reasoning now. Okay, so I should be trying to name 2/3 of what I think the average is going to be. Well, x has to be less than 100, right? There's no way that the average guess can be more than 100. So the optimal strategy of any player should be no more than 67, right? So if I think that everybody's rational, so if I believe that's true, then I think that nobody should be naming an integer bigger than 67. Okay, so what does that mean? Well, that means that I can't think that the average is any higher than 67, right? So if the average x is no bigger than 67, then I should be naming no more than 2/3 of 67, right? Now you can begin to see where this is going. So that means that if I think everybody else understands the game and understands that nobody should be naming a number bigger than 67, then nobody should be naming numbers bigger than 2/3 of 67. We keep going on this, so nobody should be naming anything more than 2/3 of 2/3 of 67. Now, obviously, when you just keep looking, everybody's going to want to be a little bit lower than everybody else's guess. So wherever the average is, you should be lower than that. What's the only number where everybody can be naming and consistently choosing the best response they have to what the average guess is? The unique Nash equilibrium of this game is for every player to announce 1. Okay, well, so we're driven all the way down to announcing 1, and that's the unique Nash equilibrium. And what happens now, we all announce 1, we all tie, and somebody wins at random. If I tried to deviate from that, if I tried to announce a higher integer, I'd just be higher than the average guess, so I wouldn't be at 2/3 of the mean. So this is going to be a stable point. Okay, so let's see what actually happens when people play this. So part of this reasoning is you're trying to form expectations of what other players are doing, and you need to make sure that those expectations actually match reality. So let's have a peek at some plays of this game. So this is a plot here where we're actually giving you the results of the online course when it was taught last year. We had players play this game, and so these are the results. And here from 2012, we had more than 10,000 people actually participate in this particular game. What do we see? So down here on this, we have integers going from 0 to 100. And then over here, we have the frequency. So how many people named a given integer. So the 50 right here is the mode. So we get the mode of 50. The most often named integer was 50. 1,600 people named 50. Well, obviously, they hadn't gone through all the reasoning, and it takes a while to sort of figure out what the equilibrium of this game is. What's the mean here? So the mean was 34. So actually, there's some interesting things. You saw some people naming 100, a number that could never really win, right? So it's not clear exactly what it could end up winning if everybody named 100. Then you could end up in a tie there, but then you would be better off naming 67 instead. So when we end up looking through this, what we end up with is some people naming high numbers, but very few people. Then we end up with some interesting spikes. A bunch of people just named 50. Not clear exactly what the reasoning is on 50. Interestingly, if you think that a bunch of people are going to do that, you might want to name 2/3 of 50. Okay, well, there's a big spike here at 33, where a bunch of people believed that other people were going to name 50. If we keep going, so hang on here. If we keep going and looking at this, what do we see? Then we see another spike at 2/3 of 33. So some people said, okay, well, maybe a bunch of people are going to think that the average is going to be 50. They're going to name 33. I'm going to go one better than that. I'm going to name something around 22, 23. You know what the winner in this game was? The winner was actually 23. So 2/3 of the average guess here was about 23. The mean was 34. And so one of these people randomly would end up being the winner of this game. Okay. There's actually a spike of people who went all the way to the Nash equilibrium. And it's interesting here because the Nash equilibrium works if you really believe that everybody else is going to name the integer 1, then that's your best response. But in situations where a bunch of people don't necessarily understand the game and haven't reasoned through it, then you actually would be better off naming a higher number. So Nash equilibrium is a stable point. If everybody figures it out and everybody abides by it, then it's the best thing you can do. But it might be that some of the players aren't necessarily figuring out exactly what goes on. Okay, now suppose you start with this game and they're not necessarily playing the Nash equilibrium, but now we have them play it again, right? So they get to do this, play it again, and then see what happens. Well, now these people should realize that they overestimated, right? There's a bunch of people here who are naming numbers too high. They should be moving their announcements to lower numbers, right? They should be moving down. And if I anticipate that everybody's going to adjust and move downwards, I should move my announcement downwards as well. So let's have a peek at what happens. So here's a subset of players actually from one of the classes I did on campus, where this is a second play of the game. So after the first play, then we have them play again. Now you can begin to see that things, the 50s have disappeared, all the numbers up here have disappeared, people have moved down, and in fact a lot more people are moving towards the equilibrium once you get to the second part, the second chance. So if you've played this game, you begin to see the logic of it, you play it again, and now we're getting closer to Nash equilibrium. So Nash equilibrium is a better predictor here if from experienced players who have played this game, understood it, and interacting with the same population, you can begin to see things unraveling and moving back towards all announcing 1. Okay, so Nash equilibrium, basic ideas, a consistent list of actions. So each player is maximizing his or her payoffs given the actions of the other players. Should be self-consistent and it's stable. The nice parts about this, each player's action is maximizing what they can get given the other players. Nobody has an incentive to deviate from their action if an equilibrium profile is played. Someone does have an incentive to deviate from a profile of actions that do not form an equilibrium. So these are the basic ideas, and we'll be looking at Nash equilibrium in much more detail. So in terms of making predictions, why should we expect Nash equilibrium to be played? Well, I think there's sort of an interesting logic here, and this logic actually goes back to some of the original discussion by Nash. When we want to make a prediction of what's going on in the game, we want something which, if players really understood things, it would be consistent. And the interesting thing is we should expect non-equilibria not to be stable, in the sense that if players understood it and see what happens in a non-equilibrium, they should move away from that. And we saw exactly that in the second round of the beauty contest game. Then people start moving down towards the Nash equilibrium. So it's not necessarily true that we always expect equilibrium to be played, but we should expect non-equilibria to vanish over time And there'll be various dynamics and other kinds of settings where there will be strong pushes towards equilibrium over time, but they might have to be learned and they might have to evolve and so forth. So as this course goes on, we'll talk more and more about some of the dynamics and things that push towards Nash equilibrium.
We'll now speak about how we predict that people will play in a game, and specifically about the concepts of best response and Nash equilibrium. Now, let's for a moment assume that you are one of the players and the other players are going to play in a way that you know. Then we can speak about what is your best thing to do, and we'll call that the best response. And technically speaking, let's use the following notation. Let's call AI the action sequence of everybody except you, player I. So it's player 1 and so on until player I-1, I+1, and all the rest. So the entire action vector, we call it the action profile, A is really made up of all those A minus I and your own action. With that notation, here's the definition. We will say that your best response, which we'll call AI star, it may not be unique, but it's got to be part of the set that we'll call BR, the best response, assuming that all the other agents play A minus I. If it's the case that for anything you might be thinking of doing, A sub I, for all A sub I, it's got to be the case that your utility for playing that, in other words, when you're playing AI star and the others are playing A minus I, for whatever it is, has got to be at least as great as anything else you might choose, A sub I. If that's the case, we'll say that AI star is a best response. A very intuitive notion, and that would bring us almost all the way there. The problem, of course, is that you don't know what the others will do. But that's okay, because we'll use the notion of best response as a building block to define what we call the Nash equilibrium. And the Nash equilibrium, briefly, is a set of actions, one for each of the agents, such that each is a best response to the others. Specifically, we'll look at an action profile here, A1 through AN, and we'll say that it's a Nash equilibrium, and later on we'll tell you why we call it specifically a pure strategy, Nash equilibrium, if it's the case that for every agent, that action, A sub I associated with the agent, is their best response to all the rest.